In our last video, we began studying the static equilibrium of incompressible fluids. That's the case of liquids. Then we took a look at these graphs and these expressions to calculate the pressure variation as we move inside them in the vertical direction. We've cited the Stevens law, which is suitable for this case. Today we'll talk about two important matters: pressure diagrams and head. But first, we'll solve some classic examples to consolidate the ideas. Let's start with this problem. A closed tank contains three immiscible liquids whose relative densities are shown in the figure. We'll assume that the air density is negligible. What's the pressure at the free surface, knowing that the pressure at the bottom of the tank is 0.1 megapascals? We mark the points A, B, C, and D in the figure. Now we can write PD equals PC plus gamma 3 H3. PC equals PB plus gamma 2 H2. PB equals PA plus gamma 1 H1. So we find PD equals PA plus gamma 1 H1 plus gamma 2 H2 plus gamma 3 H3. PA equals PD minus gamma 1 H1 plus gamma 2 H2 plus gamma 3 H3. But as we know, delta equals gamma over gamma water. So gamma equals delta gamma water. Thus, assuming that gamma water equals 10,000 newtons per cubic meter, gamma 1 equals 0.9 times 10,000 newtons per cubic meter equals 9,000 newtons per cubic meter. Gamma 2 equals 1.5 times 10,000 newtons per cubic meter equals 15,000 newtons per cubic meter. Gamma 3 equals 2.4 times 10,000 newtons per cubic meter equals 24,000 newtons per cubic meter. We know PD equals 0.1 megapascals equals 100,000 pascals. So PA equals 100,000 minus 9,000 times 2 plus 15,000 times 3 plus 24,000 times 0.5. PA equals 25,000 pascals. Okay, another one. In the device shown in this figure, the weight of the pistons A and B are 30,000 newtons and 2,000 newtons, respectively. The liquid inside the device is oil, and the specific weight is 8,580 newtons per cubic meter. What should be done to equilibrate the system? First of all, we'll see if it's in equilibrium. The pressures in the points 1 and 3 are P1 equals WA over AA equals 30,000 over pi times 0.8 to the square over 4 equals 59,683 pascals. P3 equals WB over AB plus gamma H equals 2,000 over pi times 0.20 to the square over 4 plus 8,580 times 2 equals 80,822 pascals. As P1 and P3 are different, and as they are at the same elevation, the system is not in equilibrium. We'll need to apply a force over the piston A to force equilibrium. We want P1 equals P3, so we write P1 equals WA plus F over AA equals 80,822. F equals 80,822 times pi times 0.80 to the square over 4 minus 30,000. F equals 10,626 newtons. Now we'll see a very practical problem about pressure diagrams. Pressure diagrams are the graphical representation of the variation in the intensity of pressure over a surface. It's used to calculate total pressure force and center of pressure for a submerged body, as we'll see in other videos. Engineers who deal with structural calculations love pressure diagrams. So, let's make the pressure diagram for the tank shown in this figure. It contains gasoline. Gamma gasoline equals 7,000 newtons per cubic meter. Assume that the pressure at the free surface equals 0. Okay, from the surface to the bottom of the tank, the pressure starts from 0 at the free surface and grows proportionally to the depth, as we know. And it's always perpendicular to the surface. So, the graphic representation of the pressure diagram at the left vertical wall will be as shown in this figure. Notice that at 3.5 meter depth, the pressure will be P equals 0 plus gamma H equals 7,000 times 3.5 equals 24,500 pascals equals 24.5 kilopascals. From this point to the bottom, the pressure starts from 24.5 kilopascals and grows proportionally to the depth, and it's always perpendicular to the surface. The slope of the diagram will change, as shown in the figure. At the bottom of the tank, the pressure will be P equals 24,500 plus gamma H equals 24,500 plus 7,000 times 2.5 equals 42,000 pascals equals 42 kilopascals. The graphic representation of the pressure diagram in the other vertical wall will be as shown in this figure. Notice that at 3 meters depth, the pressure will be P equals 0 plus gamma H equals 7,000 times 3 equals 21,000 pascals equals 21 kilopascals. From this point to the bottom, the pressure starts from 21 kilopascals and grows linearly with the depth, and it's always perpendicular to the surface. The slope of the diagram will change, as shown in the figure. At the bottom of the tank, the pressure will be P equals 21,000 plus gamma H equals 21,000 plus 7,000 times 3 equals 42,000 pascals equals 42 kilopascals. Finally, the bottom of the tank is horizontal, so the pressure will be the same along all its extension, as shown in the figure. Its value is, of course, 42 kilopascals. As we begin to talk about pressure diagrams, let's see some typical scenarios that we find in practice. Here is a very simple scenario in which a tank is full of water and whose free surface is exposed to the atmospheric pressure. As we did in the preceding problem, we'll assume that the pressure at the free surface equals 0. There's a linear variation of the pressure with the depth. As the bottom is horizontal, there is no pressure variation here. Now we see the cross-section of a typical swimming pool. As we saw in the preceding problem, there is a linear variation of the pressure with the depth. As these bottoms are horizontal, there is no pressure variation in these places, but we can see that there's a pressure variation in this part of the bottom. And now we see the cross-section of a pressurized tank. In the upper part of the tank, the pressure is constant and equals to P0. That's because the air density is negligible when compared to the liquid density, so there won't be any important variation of the pressure with the vertical distance. On the other hand, as long as we dive in the liquid portion, pressure starts growing from P0 to P0 plus gamma Z. As this bottom is horizontal, there is no pressure variation here. Let's introduce a very important concept, especially in the field of civil engineering, head. Here is a liquid in equilibrium. For convenience, we'll call the horizontal plane XOY the datum. We know that P equals P naught minus gamma z. From the data shown in this figure, we can write P atmosphere equals P naught minus gamma z naught. Thus, P naught equals P atmosphere plus gamma z naught. From any point P at elevation z, the pressure P will be P equals P naught minus gamma z. So, P equals P atmosphere plus gamma z naught minus gamma z, which becomes P plus gamma z equals P atmosphere plus gamma z naught. And since P atmosphere and gamma z are constants, P plus gamma z equals P atmosphere plus gamma z naught equals constant. This is a very important expression. It says that in the interior of an incompressible liquid in equilibrium, all points of the liquid have the same value for the sum of the pressure plus the product of the specific weight times the vertical distance to the datum. The expression is most used in this form. Z plus P over gamma equals Z naught plus P atmosphere over gamma equals constant. Take a look at this figure. It represents what happens in a pipe which has in its upstream extremity a reservoir and in its downstream extremity a closed valve. When we sum the height Z naught with the height abs atmosphere P over gamma, we reach a horizontal plane named absolute energy plane. As the height abs atmosphere height over gamma is the same for the entire system, we seldom account for its existence and work with the plane named effective energy plane, or in short, with the energy plane. Note that we are now taking into account the pressures as if the atmospheric pressure is inexistent or equals zero. It's okay for most practical applications. Pressures 1 and 2 are called effective pressures. Why? It's easy to understand. Take a look at this flat birthday balloon. There is atmospheric pressure inside it. But there is also atmospheric pressure outside of it. So, nothing will result. If we want to fill it up, it's necessary to overcome the external atmospheric pressure with an additional pressure, an effective pressure. This concept can be a little tricky, but you'll get used to it in no time. Let me know in the comments if you have any questions. Notice now that we can say H equals Z naught equals Z1 plus P1 over gamma equals Z2 plus P2 over gamma. H is the total head of the system. Z naught, Z1 and Z2 are elevation heads. P1 over gamma and P2 over gamma are pressure heads. There's a video on this channel talking exclusively about head. I'll leave the link in the description. Now we can see how to represent the energy plane and the pressure diagram in a cylinder containing a pressurized liquid and in a cylinder partially filled with liquid containing compressed air above it and in a cylinder partially filled with liquid but where the air above is depressed. Alright, that's all for today. In the next video, we'll talk about what happens in the case of gases. See you there! Oh, and if you like this video, don't forget to give it a like, comment, share and subscribe. Hit the bell so you can be notified of my next videos.